Okay, so number 59 and 11.1, they tell me that we drop a ball from 36 meters, and then it bounces half as high each time. And then they ask me to determine the heights of the bounces, right? Okay, so let me see. The first one, or what am I counting where it was dropped at?
36 meters.
Okay, it was counted at 36 meters. Am I counting that as a bounce or not?
No,
Probably not. That would be crazy.
but it would be half of that.
Okay, so the first bounce, right, is half that high. So this height is 18. Okay, the next bounce is half that is 9. The next bounce, right, half that is 4.5, 4.5. Let me make this easier. 9 halves. Let's see, and I was supposed to do 4. So, whoops. Here's the next one. That's 4. This height is now 9 quarters. You guys see that? So what's my system for getting between these things? Cut it in half, divide by it, or sorry, not divide by a half, but multiply by a half. So my geometric sequence that comes out of this is 36, 18, 9, 9 halves, 9 quarters. What would the next one be?
Half of that.
Half of that is 9 eighths, right? You guys see that? So if I was going to write this as a geometric sequence, what's A and R?
36.
Yeah, I started at 36, right? What's R?
No.
1/2.
Yeah.
Guys pull that? Since we've got this nice picture up here,
Yeah. Oh, that looks like the thingy.
The other one.
that's why we care about this.
Oh.
So this thingy, right? You guys see, I could phrase this as the half-life of the height of the ball. You guys see that?
Yeah.
This is really kind of, these things are all tied together, right? Anything that decays at a predictable rate, height, radioactive material, bacteria in a dish that don't decay but grow at a predictable rate. That's why I use these. These exponential functions do not go away. These are science.
Is
What's
that
that?
what's going on with Chipotle?
Yes, actually.
Really?
Yeah, E. coli and a growth media / burrito, right? Those grow at an exponential rate.
Could you, instead of using that formula for like radioactive stuff, could you use it to like, I don't know, this is gonna sound kind of weird, but like chart the decomposition of like a body or something, like.
Sure, yeah. Anything that decays at a predictable rate.
Because the drought and trees would do it that way.
Yeah. This is science. This is what we model everything with, mostly. There are a few things that don't follow this rule. Orbital mechanics doesn't usually follow this rule, but most of the kind of growth things or decay things follow these rules.
And what was the thing that ended up, if you were to like graph it, it would look like tree roots?
That's epidemiology, right? That grows this way, but instead of decaying, right, it's growing. So instead of drawing this picture, I draw the other half turned the other way.
Alright, that's too
Oh,
much.
okay.
Yeah.
Like, okay, the mouth way of this says it never touches zero, but the ball's gonna stop bouncing someday, and it's gonna hit the ground, so it's like, why, how do they do that?
So the thing that's happening here that I haven't pictured, right? I have these equally spaced, right? You guys see that? I told you that each of these bounces takes the same amount of time, right? This axis here that I've drawn doesn't represent time, it represents bounces.
But then wouldn't it slowly bounce out?
Yeah, it'll slowly stop bouncing less,
And then roll.
But-
right? In other words, the time between the bounces gets shorter. So this infinite axis that I've drawn fits into finite time, and that's the confusion. This is Zeno's paradox that you've rediscovered, actually. Yeah, so just because something takes an infinite number of steps doesn't mean that it takes infinite time.
Is it the same thing with like when you how can I say that? When you like put down your hands
Yeah.
in half and you stand. Okay.
Yeah, this is Zeno's paradox, right? So that to move my hand to the table, it takes me some time to get halfway, then it takes me some more time to get a quarter of the way and an eighth of the way, right? But those amounts of time sum to something finite.
Okay, break.
And where do we need to know that from?
I don't know, life. Don't get fooled by Zeno's paradox. What's up?
In there, it would just keep getting smaller and smaller and smaller.
Yeah, the sort of the heights of the bounces go to zero, right?
Yes.
Eventually they get smaller than Planck's constant, and I can't tell the ball's bouncing anymore. But that's a really confusing physics thing.
Okay.
Mathematically, the ball keeps bouncing.
But
The
as
ball
a-
bounces infinitely many times. Physically, you won't be able to tell. There's a
So even when it's stopped moving, it's still in mathematics, still technically moving.
the mathematical model continues bouncing, right? The physical model kind of doesn't. The reason for that is that you can't split reality into as many pieces as you can split the real numbers. This is a very deep philosophical argument. Math is not quite reality, it's just close.
Okay.
Right? It's an idea, right? We made math to model reality. It doesn't quite fit. Not everywhere, right? Most places it's good enough, but some places there's these little weirdnesses.
So like trying to put like a square block inside of a rectangle block.
I don't know. that.
It'll work a little bit, but not all the way.
Yeah, this is an approximation at best.